Hi, good morning, everyone, and thank you for joining us today. My name is Aniket Devecha, and I'm the Assistant Sales Manager for Analytics, and I'll be your host for today. This webinar is recorded, and if you have any questions, please use the Q&A tab at the bottom of your screen, and there is also a dedicated Q&A session at the end. I'll now hand over to our Director and UK and Ireland Milestone Product Specialist, Duncan Rowe, to start today's session. Thank you.
Okay, thanks, Aniket, and welcome everybody to another session, another webinar from Analytics. So today's webinar is going to focus on our UltraWAVE 3, which is the next generation in our single reaction chamber series. So when we look at our approach to microwave digestion for preparing samples for elemental analysis, we really have a solution for every sample type, every laboratory need, and every budget available. So some of you will be familiar with rotor-based platforms like the Ethos. So we have systems like the Ethos Lean, which are what we would class as entry level for low pressure, low throughput applications. And then we have our models, the Ethos Easy and Ethos Up, which are based on traditional closed vessel microwave digestion, but that allow you to work with a variety of rotors, whether that be high pressure or high throughput. And then we have our higher performers in terms of the digestion line, which is our single reaction chamber technologies. So these are in the form of the UltraWAVE and our long-standing UltraClave platform. Today's webinar is going to focus on the UltraWAVE and how we've made some new additions to this system over the years. So if we take a look back at what SRC technology is in terms of a history, is that Milestone pioneered this back in the 90s, and they filed the first patent for SRC technology in 1996. This was for the UltraClave, and this unit was essentially a floor standing system that was designed for high productivity, high throughput laboratories. So technology has been around for a number of years now. It wasn't really until 2011 when Milestone introduced the first generation benchtop SRC technology, which is the UltraWAVE 1 that we know today. This technology was using the same advantages of the UltraClave, but in a smaller platform that made it more suitable for a lot of laboratories to access. The system was really sort of designed in first mind with higher throughput laboratories for samples that people would be digesting typically in nitric acid. But due to the performance of the system and the feedback from the market, Milestone quickly moved to making a second generation platform, which is the UltraWAVE 2, with what we call the enhanced chemical resistance kit. So this allowed us to now start working with harsher chemicals like HCl, combined with nitric for aquaregia and for hydrofluoric as well. And at this point, it really changed the game in terms of the market approach to looking at microwaves and what they can do in terms of digestion. So in this time, Milestone have sold worldwide over 2,000 units. That's growing every year, and primarily this is down to the growth of the benchtop SRC and the UltraWAVE and the UltraWAVE 2. So SRC technology revolutionized what we see as microwave sample preparation today, and it was designed to overcome the limitations that we faced with the rotor-based microwaves, such as the Ethos type platform that showed earlier. With rotor-based platforms, we're relying on individually sealed vessels to be heated under pressure in a larger cavity. With the SRC technology, we actually replace the cavity with a single reaction chamber. And this chamber is much smaller in size, but it can still handle very high throughputs. The pressure rating of the SRC is much higher than rotor-based platforms, so we can go up to 199 bar of pressure. Typically with rotor-based platforms, you're working between 20 and 30 bar, sometimes up to 100 bar. But all the time with the rotor-based systems, we have to be very mindful of the applications, the samples and the chemistry that we're putting through them. We can also achieve very high temperatures with SRC technology, so up to 300 degrees. These are true temperatures compared to rotor-based platforms that, although may be able to say spec-wise they can go to 300, realistically running limits are about 220, 230 degrees with these systems. So that can be quite limiting for certain applications. So if we look at the main benefits of what SRC technology brings, the biggest one really to try and overcome the limitations of rotor-based systems was to be able to do all chemistries at once. So if you were a laboratory that had mixed samples, pharmaceutical labs with mixed APIs and excipients, or whether you're a food laboratory with lots of different food types, or just a laboratory that has many, many different samples to process, in rotor-based platforms, they have to be batched and processed a sample at a time. With the SRC technology, what we can do is place any sample, any weight of these samples, any acid chemistry we like, and any volume of the acid in a single run. So you can have upwards of 20 samples that can all be completely independent chemistries and really, really provide for the first time a revolutionary way to approach your sample preparation. So what we've managed to look at here in terms of SRC, again, is the productivity of what this can bring. So the first area that we looked to improve was the heating. So because we're working with a much smaller chamber now, we have a very, very dense field of microwaves. So typically a 1500 watt magnetron filling less than a 1 litre reactor. Now with benchtop microwaves, you are really looking at filling a 70 litre cavity or 50 litre cavity with about 1800 watts. So although they may be higher power, the dissipation between the two is much less, which allows us to have a much more focused and higher frequency of microwaves in the cavity, which allow us to heat very, very quickly without fear of going over pressure. What this also allows us to do, the way that the reaction chamber is designed, is to have a direct coupling into what we have called the base load. So again, in a rotor-based platform, you have a very large cavity that you have to ensure the microwaves are homogeneously distributed. We do that through diffusers, but also by physically rotating the vessels and the samples through that microwave field. With the SRC technology, we don't need to do that because the antenna is located directly underneath the reaction chamber, and it will couple with the base load and the acid and the samples within there. So it's a very, very homogeneous field, very, very evenly spread, and extremely easy for us to heat quickly. We can also cool very quickly by having a dedicated chiller attached to the platform. What the chiller does is to cool the outside of the reactor to maintain a very cold temperature. And this means that at the end of the run, we can use this chiller to cool extremely quickly, even from very high temperatures. And then to improve this further, we can automatically depressurize the chamber so that the user doesn't have to do this themselves. So by increasing the rate at which we can heat and the speed at which we can cool, we're shortening the runtime significantly compared to rotor-based platforms. Increasing productivity further, we looked at a way of simplifying the handling process and the design of the vials or the vessels. So anybody that's worked with rotor-based systems will know that the higher pressure systems and even the medium pressure rotors have multiple parts to them. So you have typically a vessel, a cap, a cover, a shield. With the higher pressure ones, you will have a pressure screw, you will have to hand tight, or you will have to torque wrench the platforms down. With the SRC technology, it's a very, very simple method of dropping a loose fitting cap onto a wide range of materials, whether it be TFM, quartz, or glass. We have these of variety in sizes of racks and volumes to suit the application, but it shortens the handling time at the front end of the workflow and at the back end. So it's making it a much, much faster and streamlined process. And also, as I mentioned, we can do any chemistries at once, so we have no sample batching at all. Any samples that come through the door, we can put straight into the Ultra SRC and go on. So when we look at this in terms of a case study, comparing it to other areas of microwaves, whether this be a high throughput rotor, a high performance, or a high pressure, we can see that the single reaction chamber can process significantly more samples in a typical 8-hour shift. Where the SRC becomes even more productive is when we mix up the sample batches. So you can see from this first slide here, this is if we're running the same sample type, which means that you can do high batches with the rotor-based systems. When we move to mixed sample batches, you obviously can't process as many in rotor-based platforms, but the SRC technology remains unimpeded, so it can still offer extremely high throughput. We've also seen that we can work at much higher temperatures. So the higher the temperature really means the better the digestion quality, because the more that we can treat these samples at higher temperatures, we reduce the amount of carbon that is going to be present at the end of the run. If you're working with ICP-MS, higher carbon contents can be an issue in terms of polyatomic interferences on the ICP-MS, and also higher the carbon content, the higher the deposits will be on your cone. So there's more maintenance you would have to do with the ICP-MS. So if we can work with a higher temperature without having to worry about the vessel technology we're using, we can give a much better digestion, much more reproducible, and obviously a much cleaner solution to go into your ICP. Other benefits of high temperature are to allow us to successfully digest very, very difficult sample matrices. So some of the samples that we've faced during the last sort of 20 years of SRC technology can tend to be very difficult to break down. These will require often very high temperatures, so in excess of 260 degrees. Though it wouldn't be possible in rotor-based platforms, but with the SRC technology, we can work up to 300 degrees if needed. By working at higher temperatures, we're also able to work with more dilute acids. So again, because we don't have a fear of consequence of going over pressure, we can work with weaker acids, but take them to higher temperatures. So this has a significant impact on the LOD and obviously the ratio of sample to acid that you're using. So again, it'll further improve the results of your ICP. Now, the reason why we can work at such high temperatures is down to the high pressure stainless steel reactor jacket that we have on the system. So there's a 900 mil Teflon vessel that sits inside this 990 mil stainless steel reactor. So this reactor is replacing the shields that you would be used to in a rotor-based system. And because obviously it's made of stainless steel, it can maintain these very, very high pressures up to 199 bar. Because we can maintain the high pressures, that allows us to get up to these high temperatures, because we are taking acids far in excess of their boiling point. So they create huge vapor pressures. In traditional rotor-based systems, they would vent at certain limits, but with the fact we can go up to 199 bar, we have no fear of doing that. So it significantly increases the safety of operation. It improves the recoveries as well, because we're not having any venting occurring, which means we don't lose any analytes during the digestion step. It will allow us now to process much larger sample masses of organic materials as well. When we break down organic samples in a closed vessel, it generates decomposition gases. So again, in rotor-based platforms, we have to be mindful of the amount of sample we process so that we don't go over pressure. Within the SRC, that is no longer an issue. So we can work with very, very large sample masses, grams of certain materials, as opposed to having to keep it down to maybe half a gram or 0.1 of a gram or even lower in the rotor-based systems. This also allows us to work with very reactive samples. So things like oils, petrochemical samples, high fat samples with food, anything that's going to generate large volumes of gas when it breaks down. These reactive samples can be processed safely and reproducibly under the SRC technology. So how does it work? Well, the principle of operation is we place our rack that contains the vials into the base load. So for the vials, we simply weigh in the sample and add the acid, whatever the chemistry that we're looking to do. We place this into the base load, which consists of 150 mils of deionized water and 5 mils of nitric acid. So the goal of the base load is to help us in terms of the heating and controlling the temperature as well. So you can see at the bottom of the chamber there that the antenna is coming directly up underneath, and it's going to be 2 or 3 centimeters below the base of the reaction chamber. So this means that we've got a very, very direct form of heating, and the base load itself will act as a water bath around the vials. It will absorb the microwave energy, and then it will dissipate that around the vials, giving it a very, very even field temperature. So What this allows us to do is to control things like exothermic reactions very closely, but it also, at the end of the run, when we do release the pressure from the run and during the run when NOx vapors are generated, the base load will absorb a very large portion of these, which means that there's very small amounts of NOx vapor that will be going through the exhaust of the system and out to your fume extract as well. So once we've loaded these into the chamber, we will do the only manual part of the operation, which is to close up the clamps at the top. There are safety switches all around the SRC technology to make sure that it's all closed. And if it's not in position, it won't allow the next stage to begin. So presuming that everything's been closed properly, we then load the nitrogen into the system. So this pre-pressurization step is the critical part of SRC and is the reason why we can work with mixed sample chemistries. So we have loose fitting caps on these vials that have a hole in them. So when we're loading the pressure into this sealed chamber, typically at 40 bar, it creates an equilibrium because the pressure will go inside the vial and will be the same outside of the vial. So we start with an equilibrium point, regardless of the acid chemistry that we're using, which means that we're never going to have any boiling of the acids, which means we don't get any cross-contamination or loss of volatiles skipping from vial to vial. So the pressure inside the system, we know that the chemistry-wise how this works, and I'll show you by using water as an example. So obviously the boiling point of water at atmospheric pressure is 100 degrees. So if we were to load in 40 bar of pressure, so we pressurize the SRC chamber with 40 bar at room temperature, what this does is to shift the boiling point of water from 100 degrees up to 250 degrees. So we've created a buffer here for when we do start to heat. So when we do actually apply the microwaves and increase the heat up to 250, the vapor pressure of water increases as well. And at this stage, it will be at 60 bar of pressure. And under these conditions, water wouldn't then boil until 270. So we are not near the boiling point of water. This means that we can apply this across all of the acids that we'll place in the chamber as well. So we can ensure that whatever we're heating, we're not going to get this boiling or spitting or transference of any of the analytes from vial to vial. So once we've pre-pressurized the chamber, the microwave run will automatically begin. So it will go onto the designed heating profile that the end user has suggested, and that will typically be a ramp up to a goal temperature and then a hold time. Now, as I said, these microwave programs can be very quick, but there is also the ability of the SRC to work for very, very long periods of times at high temperatures as well. So once your microwave program is done and the sample digestion is completed, we move on to the next stage, which is to be cooling the chamber and then to obviously open the vials themselves. So as we have a recirculating chiller attached to this system, there's a jacket around the chamber which is cooled periodically during the run to maintain integrity of the larger Teflon vessel. But at the end of the heating profile, we basically allow this cooled water to constantly be recirculating around the reaction chamber, which means we can cool extremely quickly. So even if we are at high temperatures, say of 270 degrees, we can cool down to 80 degrees in just 12 minutes. Rotor-based platforms, because they've got a larger cavity and they've got individually sealed vessels in there, we have an airflow that comes across the chamber. Now, this cooling period can be 30, 40, 50 minutes sometimes. So reducing this down to 12 minutes is a significant reduction in the overall workflow. What we do additionally as well is to release the pressure from the chamber. So as soon as we hit 80 degrees, the software will trigger the release of the valve automatically, and it will open it at the set rate, depending on what the user has placed this at, typically 6 to 8 bars per minute. So what this is doing is to depressurize the system so that when the user comes to remove the rack and the vials from the chamber, it is ambient conditions. So at 0 bar pressure, and that it is down typically just above room temperature. Now, with rotor-based platforms, we typically suggest that most people will take them out of the chamber at 60 degrees, and then they will take them individually into the fume cupboard and they will depressurize them manually. So not only does this increase the handling time significantly, it also increases the user exposure to acid vapors as well. So the SRC really is removing a complete step from the workflow. So what this means in terms overall is the increased productivity through the fact that we can mix sample types in the same run. So we don't have any batching of samples. We can run whatever it is that's come in for us. We can significantly reduce the microwave run by reducing the heating and the cooling stage. We reduce the handling by having simpler to handle vials, but also to have the automatic depressurization at the end of the run. We have also got the option to use disposable glass vials should they fit your application, which means we can eliminate the cleaning side of things as well. And because we can work at higher temperatures without fear of going over pressure, we can really have one method fits all. So if you're a laboratory that has a lot of mixed sample types that some will digest at 180, some at 220, some at 230, we can just work at the highest temperature and treat all samples the same. It makes it a lot easier from the user perspective. Performance is obviously far superior compared to the rotor-based systems, and we've seen this through the fact that we can work at much higher temperatures, which gives us a better quality digest and more reproducible digest. We can process much higher samples and more reactive samples due to the fact that we can operate at these high pressures. And we've significantly improved the LOD, which is a really key part of the SRC brand, because ICP-MSs every year have got more sensitive, regulations have got more stringent, so it's put a lot more pressure on the front end in terms of what sample preparation need to do. By the fact we can work with dilute acids, we can improve here. We can work with lower blanks, so we're no longer dependent on having to work with, say, 5 or 10 mils of acid. We can work with very, very small amounts, which means we can also process very, very small sample sizes as well. So certain applications within the SRC, for example, can work with micrograms of sample with microliters of acid. And the reason we're able to do this is thanks to the base load and the fact that we have an equilibrium and the same temperature and pressure across all vials during the run. We can also now handle these very difficult matrices that weren't possible in traditional microwaves before. So anything that needs very high temperatures for very long periods of times with complex acid mixtures, the SRC really is the only way to be able to process these samples. So we come now to the UltraWAVE 3, which is obviously the main point of this webinar. So this is our third generation of the benchtop SRC technology. So we've taken all of the benefits that we've gained from the decades of experience with SRC technology and look to see how we can improve that to meet the demands of the market today. So when we look at what's new in the UltraWAVE 3, there are quite a lot of things. Obviously, visually, it is different. The footprint is very similar to the UltraWAVE 1 and the 2, so that's not changed. But in terms of the design and the layout of the platform, it has changed quite dramatically. But there are 7 key areas that I want to focus on today to show people who may be familiar with the SRC technology where it's gone, but also to highlight where we've improved for those that aren't necessarily operating with the system now. So the first area that we look to improve were the racks. So the racks really replaced the vessel component of rotor-based platforms. So they typically are what take the brunt of the acid conditions or the samples that we're running. So we had to look at trying to improve the performance of these racks further. And we've done this by making them much more rugged in terms of the build of them. So we've increased the mechanical properties, thermal stabilities, by making the racks thicker in certain components of it. So when we had these Teflon racks previously in the UltraWAVE 1 and the 2, there wasn't a very big gap between vial to vial. And what could occur over time if you were either operating at high temperatures is that the Teflon could become soft slightly, and it could sometimes either fuse or it could not catch next to the other vials, and it could cause the vials to reduce in terms of their lifetime. Now, what we looked at here was to increase the ability of the base load to mix around in between these vials and within the rack itself. So there's a hole in the base of the the rack, and there's a greater area between the vials, which means that we can get a quicker equilibrium. So if we are working with very reactive samples or with high sample masses in there, sometimes the equilibrium can take a little bit to catch up with itself. With the fact we've got a greater coverage of this base load around it, it means we can control this much longer. Much quicker, sorry, and it creates a much longer lifetime of these racks and the vials themselves. We also look to make the handling of them a little bit easier as well. Very simple design here was to create 2 pins into the bottom adapter. So what this does is essentially just push up one from each of the rings to allow the user to get their fingers on it much easier to remove it from the rack. And then what we also looked to do was to try and increase the productivity. So as we said, ICP-MS is always putting pressure on sample prep on the front end. So we always have to be able to process more samples and faster. So we wanted to do this, but keep the same performance of the previous models of the UltraWAVE 1 and 2. So we can still operate at the same conditions as we could previously, but now we've increased the main racks that we have worked with from 15 up to 20 and the 5 up to 7. So these have now given us a much higher throughput for the laboratories that were working with the traditional racks. We've created a couple of new racks for smaller vials, so for 27 and 40. But we also do have the option to make bespoke racks based on what a specific customer may need. So we can make these in 9 position. There may be other ones available on the market, but all of them will have the ability to work with the mixture of materials that we have available to us. So they'll be available with Teflon, with quartz, and with glass. And it's important to note that obviously within here with the UltraWAVE 3, as you can with the UltraWAVE 1 and 2, you can even mix and match this during the run. So you could have 10 vials of Teflon and 10 of quartz, for example. So in terms of the racks, obviously we've looked at increasing productivity. What we also looked moving forward was trying to improve the longevity and the accuracy of the chamber itself. So the first part is the temperature sensor. Now, UltraWAVE 1 and 2 used what we call a single point temperature control, which was essentially a thermocouple that was placed into the base load. We have now moved away from this to a bulk temperature measurement, and we are using the technology that we've used on our rotor-based platforms called EasyTemp. So this essentially is an infrared sensor, and this is looking at from the base of the reaction chamber, and it's giving us a much wider surface area to read. So instead of having a single point where we're reading the base load, we've now got a bigger area, which gives us a much greater control over the reaction and allows us to regulate the microwaves much faster, because the way we process like we do in the rotor-based platforms is via time and temperature, and then the feedback we get from the temperature sensors dictate what microwave power is emitted into the cavity. If we can control the temperature much faster, we can control the microwave power and use less energy still. So it's a much more faster way to recognize what's going on with the cavity. And because we have now removed the thermocouple, we've actually managed to remove, obviously, the thermowell and the ability to have to place these protective sleeves if a user was working with HF. So what this means for us is that we now can plug the racks in much quicker, because on the UltraWAVE 1 and 2, you used to have to hang them into the top of the reactor and then align them to make sure that it was in line with the thermocouple so that it wasn't offset. And what this has meant really is a lowering of the maintenance costs. So because we've removed the need to have a thermocouple, we don't have to look at replacing the thermowell, which we did on an annual basis. We also don't have to look at any HF tips, which were consumable as well. So it's really bringing down the maintenance costs for all customers, but also significantly for anyone that was working at high temperatures and high pressures for very long periods, who sometimes would have periodic service visits to replace this item. The fact we've removed that now, obviously reduces a lot of the maintenance costs associated with that and makes it a lot easier for the user to get the racks in and out of the chamber. So moving on to the chamber now, the reaction chamber itself has been redesigned. So we've optimized this to allow essentially for a shorter and wider Teflon vessel. So it's still 900 ml vessel, but as you can see, we have made it shorter than the UltraWAVE 1 and 2, but we have kept to the same pressure limit, so 199 bar and 900 mil, and this keeps us under the PED directive limit, but allows us to put in these higher capacity racks because we physically have more space to work with. What we've also done is to look at changing the base of the reactor. So the UltraWAVE 1 and 2 as standard come with a Teflon bottom plate, and that bottom plate sits over the antenna and protects the antenna and the base of the reaction chamber from the 900 ml reactor. Now, what could happen again on platforms where you're working at higher temperatures, or if you have just been running the system for a long period, is that there can be diffusion from some of the NOx vapors through the Teflon vessel and into the TFM base plate. If the base plate starts to absorb some of these NOx vapors, it will then start to absorb microwave energy as that's emitted into the chamber. What that can cause is a superficial heating of the antenna. We always track the antenna and magnetron temperatures to make sure they're not overheating. So what could happen is when the base plate was contaminated, it would switch off the antenna, which would abort the run. So when we looked at a workaround for this with the UltraWAVE 2, we introduced a quartz bottom plate. So the quartz bottom plate wasn't susceptible to microwave absorption or any of this diffusion of the NOx vapors. And that did lower the cost and the maintenance in terms of what the UltraWAVE 2 had. So we've taken that and now put it as standard in the UltraWAVE 3. Now, this one differs slightly because we've obviously accommodated the new temperature sensor in here. So there is a window for which the Easy Temp sensor could look through. But this quartz bottom plate really does ensure a longer lifetime and the ability to maintain these high temperatures for very long periods of time. What we've also done to help the end user is to make it easier to actually remove the liner from the reaction chamber. So we can do this by simply pressing on a button as an icon on the system page, and this will push some residual nitrogen up to create pressure to pop it up for you so you can easily remove it and take it away. What we've also added is the capability for stirring. Now, this is an option. It's not standard on all systems, and we haven't put it standard because there's not too many applications that do benefit directly from stirring. But there are certain ones if you're working with quite viscous liquids that you're trying to digest, so oils, fats, for example. If they were to stick to the vial wall, the stirring can help to aid the digestion by ensuring that the sample is still in contact with the acid. So it's not a big application area, but it is something that can be added on to the UltraWAVE 3. The next area we looked at was the high pressure line. Now, the high pressure line is the critical component of SRC technology. It is the part that controls the flow of pressure from the chamber to the high pressure valve that's located in the rear of the system. So it can directly impact on a number of areas. And from the analytical side of it, it can impact on the ability of working at very trace levels. It can also impact on the daily cleaning that a user may have to do and the total cost of ownership, as well as obviously safety. So Milestone as always look to gain feedback from the market to see what areas we can improve on. And they did this first of all through the introduction of the UltraWAVE 2, which was to bring in this enhanced chemical resistance kit, the ECR. That essentially was to change certain components within the UltraWAVE 1 to allow them to be resistant to acids like HCl and HF. The high pressure lines themselves as well have to be replaced annually on the UltraWAVE 1 and 2. So we wanted to try and look at a way to improve this whilst also keeping the main advantages of our design. So we've always had the inlet and outlet lines separate, and there is a big reason for this, which we'll come to. But essentially, it allows us to have a much more efficient cleaning and a superior blank, because we're not getting any residue or carryover from run to run. So when we redesigned the pressure lines, instead of having flexible tubing that we had on the UltraWAVE 1 and 2, we've developed these high pressure manifold for the outlet, so it's a wider source to get the waste gases out at the end of the run. But we've also put a high pressure tube from the inlet that is fixed onto the reactor cavity. So these move up and down as the reaction chamber does start the run. We have made the UltraWAVE 3 and ECR as standard. So everything within the ECR internally is available, is got the ability to work with these harsher chemicals like HCl and HF. This gives the system much greater stability and durability. So the lifetime of the system is improved further, and it has reduced the maintenance significantly for the end user, and also from a annual service point of view. So if we compare what it used to look like, the UltraWAVE 1 and 2 used to have the pressure in and pressure out, so the blue and the red lines that we can see indicated on the picture here. And these would be introduced into the reaction chamber by these little plastic pins coming in. So these were directly above the same vial position every time. So when the vial rack was placed in the cavity, it would be located next to the thermowell based on its position. So typically it would be the number 1 or the number 2 position, would be having the nitrogen straight above, being forced down above it. And then you would have the exhaust going out above, normally number 3 or 4. Now, because these tubes were plastic when they were coming in, there was potential for blockage, because when they could get too hot, they could sometimes contract a little bit. So you wouldn't either get the requisite pressure coming in or the escape of the pressure at the end of the run. It also meant, because they were vertically aligned, that they required a lot more flushing to force through or out anything that may be sitting between the valve and the reactor cover. And as this was the case, we had to replace these on an annual basis as part of the PM service, and also had to ensure that run to run that customers were doing flushing and making sure they were performing this at the end of the run, or certainly on a weekly basis. Now, what we looked to change on this, as I said, is to optimize basically the inlet of the gas. So the one we can see here with the blue arrows is the gas in. So instead of it being a single point coming over one vessel, it's actually split in 5 different directions. And this allows a greater dissipation of the gas when it's pre-pressurizing. So there's no direct exposure of any of the vials to the gas being forced on top of them. We've got horizontal lines in there now as opposed to the vertical ones, and these do not have to be replaced on an annual basis. In fact, we wouldn't expect them to be replaced even on a 2 or a 3 or a 4-year basis. This has extended the lifetime of the reactor significantly, and it's also reduced the running costs as well, in terms of the maintenance packages, which we'll see later on. So if we look at how this is in terms of operation, there are 4 stages to the way the mechanics work. So the first is obviously the nitrogen loading, and this is showing here that we've got a greater dissipation of the nitrogen coming into the cavity. During the run, there's a good homogenization of the overall pressure in there. And then thirdly, when we come to finish the run and release the pressure, we've got a much wider gap for the NOx vapors to come out of. And then as a 4th stage, we do the automatic flushing. So as I mentioned, on the 1 and the 2, it's not standard to have a gas module or a loading device on there. It is now automatic and built into the UltraWAVE 3. So the user doesn't even see it or have to accommodate it on the bench. And what this does is basically ensure that the pressure line, so the out, does not have anything left in it when we come to do a next run. If we were to have just one inlet and outlet line, it would mean that you were constantly bringing back in any of the contaminants from the previous run. So we offer a much superior blank operating this way and a much more efficient cleaning and flushing of the reactor itself. So next up, we looked at microwave efficiency. Now, we've moved here to the first ever liquid-cooled microwave magnetron. Now, the previous magnetrons in the UltraWAVE 1 and 2 and in the rotor-based platforms, they are cooled by quite heavy-duty fans, because the magnetrons, when they're on, will generate quite high heat. So we have to make sure that the magnetron doesn't overheat, and we have large fans to do that. So we've moved away from that for a couple of reasons. The first is to get a better cooling efficiency. Now, we found that a lot more applications were moving more with the UltraWAVE to wanting to work at high temperatures for longer periods of time. That places extra load on the magnetron because it's generally working at a high power for longer periods. And this can cause obviously a lot of heat around the magnetron and more sort of supply from the fans to have to cool them. With the fact we've now got a water-cooled magnetron, it means that we can deliver this high power constantly for much, much longer periods of time, but also keeping the lifetime of the magnetron and the high voltage components much longer. So we use the same chiller that we use to cool the reactor. So we just tee off inside from there. So a portion goes around the reactor and a portion goes to the magnetron. And this is the reason why we have a dedicated chiller, because it allows us to obviously reduce footprints further, but also to reduce the stress really on the high voltage components of the microwave. So not only does this improve efficiency and allows us to run for high temperatures for longer periods of time with less stress, it also reduces heat into the laboratory. So many people that have worked with microwaves may have experienced that if you've got one of them working at full power, the fan is basically removing that heat and pushing it out of the chassis. So when it's doing that, it's pushing it into the laboratory. So the fact that we've removed that now means that we don't have any heat dissipating into the laboratory from the UltraWAVE, and it also means that we've got pretty much silent operation, because really the main source of noise coming from the UltraWAVes, or from any microwave for that matter, was really the fan that was working to cool the magnetrons. So we've gone from having something like the UltraWAVE 1 or 2, which may have decibels of around 63, down to 48, so just above background noise at 43 decibels. So it is almost a silent operation. So it's improving the laboratory environment through heat, but also through the reduced noise as well. So next up, like anything, is obviously user interface. This is always changing. So we looked here to move away from our typical terminals that are located outside of the chamber and connected to the microwave via LAN cables, to integrating a tablet into the chassis itself. So again, this is saving space in terms of from the bench perspective. It's a bigger screen as well, so it's a 10.1 inch screen that is diagonally pivoted backwards to remove any glare that may be from lights in the laboratory. As you'd expect, it's a color, it's touchscreen. It's got multiple USB ports to allow us to extract data if we need to. And also it's got the LAN connectivity if we want to network it to a dedicated network or a platform. And we've also got additional connections of here where we can connect up an external balance. So if you wanted to transfer weights directly across, you can. We've got the option for Wi-Fi. So if you didn't want to work with an Ethernet connection, you can add the Wi-Fi as an option. And then we've also recently brought out the ability to work with a barcode reader. So this can be connected up to the UltraWAVE 3 as well. And it can be part of the traceability of your samples as they move through the workflow from start to digestion to analysis. So with the terminal itself changing, we've obviously updated the base software, which is Easy Control 3. So we can customize the home screen now. So previously users would just operate based on a set layout. You can now choose to have whatever you want, shortcuts to specific areas that may use, say the PDF or Milestone Connect or a dashboard. All the while, you will have a sidebar that shows the digestion conditions if you are in a run mode. So you can see what's going on with the run and have a run going, but also utilize some of the icons that are built into this platform. And this really was designed because we wanted users to be able to make the most out of Milestone Connect. So people aren't familiar with Milestone Connect, this was a web-based platform and still is for previous models. And it allows users to look at tutorial videos. So this may be of how to put a vial and rack together, maintenance procedures for the UltraWAVE, how to handle the racks, how to perform cleaning. All of these now are built into the terminal themselves. You can also look at technical documents. So there will be user manuals in there. There will be technical notes to look for the spare parts. And there'll also be tips and techniques that go through standard operating procedures of how best to work with certain samples or how to perform user maintenance. What we also now have the option for is this remote easy control connection. So if it is obviously allowed from the user end, we can basically log in to your system by taking over similar to something like TeamViewer, where we can go in and take a look at the run data, the trail data, any errors that may be formed. So the full history trail, and allow us really to perform remote diagnostics to see if or what has occurred on the UltraWAVE 3. You've also got sample and system status dashboard. So this will show you how many runs, how many pressure cycles have been performed on there. We've also got different layouts, so you can have it in the standard layout or in dark mode as well. And we've introduced a system status indicator that will show us very nicely visually at what stage of the digestion it's at. So basically the whole back chamber is backlit, and it will be red for heating, blue for cooling, green for complete. So you can very quickly and easily see across the lab as to where we're at. So the last part in terms of the UltraWAVE 3 is the maintenance approach. Now, we really have designed this system for longevity. So we have taken all of the feedback from the market over the last 20 years or so, looked at what we can improve, what we can make more robust, and what we can make easier for the user. So we've obviously done this, as we've talked about, with things like the high pressure line, making them more robust, adding in automatic gas flushing to make a cleaner digestion and longer lifetime of the gas lines, moving to an easy temp technology to completely eliminate a certain portion of the maintenance for the user and from an annual perspective. Putting in a standard things like the quartz bottom plate, which reduce the contamination and increase the lifetime of all of the components from the high voltage side. Bringing in unique technologies like water-cooled magnetrons to again improve the lifetime of the components, and generally making even the consumable side of it more rugged, so giving us a longer life out of the small consumable side of SRC. Now, with anyone that's had an UltraWAVE 1 or 2 and is familiar with the maintenance side of it, it was an annual visit where we would replace certain parts of the hardware. These would include pressure lines, rupture discs, base plates, seals, O-rings, etc. For the first time now, we've moved away from having sort of rigid PM contracts to having more bespoke plans based on our experience over the last 20 years or so. So what this was aimed to do was to base it more on an individual customer basis, and it would we would look at the type of samples that people would be running, the estimated usage, which we can obviously track through the dashboard, and really basing what the parts would be required for this, rather than having a routine replacement of certain things like the pressure lines and pressure discs and so on. So what this is doing is reducing the amount of visits we need to make to certain customers, but also lowering the total cost of ownership, because the maintenance plans will now be on a case-by-case basis. So if people are working with easier samples to digest on lower throughputs. They won't need certain things changing for years at a time. But even people that are working at the ultimate end of the limits of the UltraWAVE 3 is that this cost of ownership will still come down significantly. So if we summarize the improvements, obviously there's quite a lot of them here. So we've got obviously higher productivity, not just through having higher capacity racks, but also from the fact that we can flush the chambers automatically, and we've got a much more efficient way of heating. We've got a high performance in terms of the improved ability to control the base load and the homogeneity of the temperature and the pressure inside. We can work at these higher temperatures even more so from the 1 and the 2 to the 3 now, because we can obviously control the temperature of the magnetron better. We've got lower blanks, so we're improving obviously, or limiting the cross-contamination from run to run. A much better control of the temperature. Safety, although was extremely high with the 1 and 2, was improved even further with the fact that we've now got the easy temp temperature control instead of a direct sensor, and that the pressure lines are much more rugged in terms of their lifetime. Working conditions have improved because we've obviously lowered the operator time required for certain maintenance procedures, making it easier to remove the liner and the vials, reducing the noise and the heat that comes into the laboratory. Usability is improved because the racks themselves are easier to put in and out of the chamber. Automated functions, as we said, with things like the flushing. Software has improved, larger display, easier to use. More access to the information in terms of tutorial and the things that Milestone Connect can bring. And obviously, lastly, the total cost of ownership being brought down by the fact that we've made all of these things that we saw increase the lifetime on the UltraWAVE 1 and the UltraWAVE 2 standard, but also bringing in these additional things like removing the temperature sensor, higher pressure lines, longer life for all the high voltage, and these new PM plans. So hopefully, for those of you that are familiar with the 1 and 2 and have used it, you can see obviously where we've come from in terms of making these amendments. We've also tried to look at improving the workflow even further by bringing in a newer technology. So this is a standalone technology, but I'll only spend a minute on it. But essentially, we introduced to market last year what's called the Easy Fill. So the Easy Fill is an automatic acid dosing station. So it can hold up to 6 bottles on the top. So typically 5 acids and 1 for water for rinse. And we have a 6-channel peristaltic pump that will take the required volume of acid based from the software and dose it into your microwave vials. So there's a peristaltic pump and an XY auto sampler on there. We have universal bottlenecks, so you can use the GL45 adapters, which can go straight onto your acid bottles. So it makes it very easy in terms of installation and for changing over from your acids. The software itself will control things like auto rinse, check the reagent stock, the waste volume. We've got the ability to work with multiple racks and vessels. So although we're talking about this as part of the UltraWAVE 3, this can be used for any Milestone vials and any of the legacy vials or vessels that we've got. But it can also accommodate bespoke racks. So if you are using other microwave platforms or you're using DigiBlocks, you can still use the Easy Fill for this. We would just have to set up the rack dimensions and calibrate it for you. So it really does fit very nicely in terms of the way we're trying to control and optimize this workflow, because it's improved safety significantly because the user is no longer having to pipette these in or use Winchesters themselves to put it in. And it also improves reproducibility massively as well. So when we look at the SRC product line, obviously we've got the 1 and the 2 that are still available, as is the UltraClave. We've now added the UltraWAVE 3 into this, and to further improve the product line, not just for the SRC, but for everything, we've introduced our Easy Fill platform. So that covers everything in terms of the new additions that we've made to the SRC platform and our digestion line as a whole. Just before we head to the Q&A session, I just want to spend a very quick couple of seconds on Lab Innovations. So those of you that aren't familiar, Lab Innovations is the biggest trade show for the laboratory industry. It's held on the 1st and 2nd of November at the NEC in Birmingham, Hall 2. It's free to attend. Analytics, as always, we are there. We're on stand G80. Now, we will have the UltraWAVE 3 and the Easy Fill, plus all of our other technologies down at Lab Innovations available for demonstration. So if it's something you want to see in the flesh, have a look at, it's a very, very good reason to come along to the show to see, obviously, ourselves. But also there are, I think, upwards of 190 other vendors that will be there. So you can make certainly a day of it coming out to see everybody there. Now, Analytics are the VIP sponsors of this event. So if anyone is interested in coming, you can pop your name or contact us after, pop your name in the Q&A or the chat box, and we can send out a specific link for you, which will allow you to register as a VIP attendee. So what you get as a VIP is access to a dedicated lounge. So there's some very nice seating areas in there, free coffee all throughout the day. You'll get entered automatically into a prize draw, and some of the things you can win at the moment, things like spa days, iPads, PS5s. There'll be breakfast served, which is complimentary between 9 and 10:30 on both days, and happy hour drinks on both days, complimentary as well, between 2 and 3. You'll also have the opportunity to meet the exclusive speakers, Maggie Philbin and Rosa Espinoza, who'll be speaking at the RSC Theatre. So if you are planning on attending, obviously, let us know. We can get you signed up as VIPs, and you can come along to the stand and meet all our wonderful people and see all the wonderful kit we've got. So thank you all very much for listening. I'm going to hand back to Aniket now just to see what questions that we've had.
Yeah, sure. Duncan, thank you very much for that very interesting presentation. We do have a couple of minutes left to cover a few questions we've got. And for any other questions we can't get to on this session, the relevant technical representative will come back to you on an individual basis. So this question's from an existing user, it seems, and they're asking, can we use our old style UltraWAVE vials and racks in the newer UltraWAVE 3 model?
Yeah, the answer is no. The racks, because we've redesigned obviously the reaction chamber, so we've made it shorter and wider, the vials for the UltraWAVE 1 and 2 will be too tall for the UltraWAVE 3, so you wouldn't be able to take those and put them in the UltraWAVE 3. Okay.
And this is a question, can you run our samples as a proof of concept?
Yes. For anything we offer, we've got a development lab here where the UltraWAVE 3 is. So if people are wanting to test certain samples, maybe something they're struggling with or something new, you can send it up to us. It's all free of charge, our method development, so we can run it here, optimize the conditions. So if it's something you're doing at the moment, we can look to keep it to a certain platform, whether that be the UltraWAVE 1, 2, or even an ethos system. So yeah, I would just urge people to speak to their technical reps for ourselves, and that they can submit them free of charge.
Okay, and Duncan, we've got time just to cover this one last question before we can end the session, because it is now 12 o'clock. So as a final question, what is the expected lifetime of the digestion vessels typically?
Yeah, I mean, it depends which ones you're using. The glass ones obviously are designed for being disposable. So although they are single use, you can actually reuse those and bake them out and clean them. Quartz ones, we would typically say will last thousands of runs unless somebody physically broke them. It mainly is Teflon vessels with microwaves that tend to have a slightly shorter lifetime. but that is based on rotor-based systems because they generally are under quite high pressure. With one of the benefits with the SRC technology is that we've got the same pressure inside the vial as we do outside, so it doesn't stress the Teflon anywhere near as much as people may be used to from rotor-based platforms. The Teflon is more absorbent to things like NOx vapors transferring into it than quartz or glass would be. But typically we would expect, if you're working at a mid-range temperature of anything 250 or below, they should last you thousands of runs still with the Teflon. Obviously, the higher the temperature for the longer period you go, that will drop it down a bit for you. But if we're comparing it to rotor-based systems, they will last significantly longer.
No, Duncan, thank you very much. As mentioned, with time, that's what we have time for now. However, any pending questions will come back to you on an individual basis. So again, thank you everyone for joining us today, and thank you for listening. And if you do need anything, feel free to contact us, and we'll come back to you as quickly as possible. Thank you very much.
Thank you.